Alright, in this section we're going to be discussing the next part of the firmware, which is of course implementing the closed loop control system. Specifically the function that will actually, implement the closed loop control system, i.e. change the duty cycle based on the sensor inputs. And for this, I like to think on a more broader scale for this next part. Sort of in terms of coding it, um, coding the firmware in such a way that it's easier to use it on other families, i.e., with the use of a function and or a separate file that you actually call to implement the controller. Of course, using this on a different microcontroller system, like another family, like for example NXP or Texas Instrument, of course you would have to initialize the peripherals differently there. But coding the actual control system is a lot easier because you're basically just going to copy and paste a certain file and change the duty cycle update, and of course the ADC aspect, updating it from the DMA as you should. But that's about it. So the first step to do that is basically to first off to create a header file. So the code stays the same as it was from the previous section. So now you make a header file, and I like to give the header files names something simple like custom.h, because it's a custom file. And in custom.h, all I'm going to do here is I'm going to define the function that we're going to be utilizing. So it's a void function. It's not going to return anything, and I'm sort of doing that on purpose. It might be a bit, I don't know, perhaps it should return the duty cycle, but I'm sort of trying to reduce the amount of time it takes. So I just wanted to implement everything in the function. So I'm just going to say, name the function cntrl routine, and it's going to be void argument as well. I'll just go there, do that, all caps. And the next step up to this, let me just save that. The next step up to this is you want to make a custom.c file to go with the header file. Let me just go to new source file and custom.c. You want to sort of finish that off, and this is where it gets kind of interesting. First off, I'm gonna make the function. Of course, there's a lot to do with it there. Of course, there's a lot of variables that need to be implemented here. But anyway, this is it for now. The variable implementation, the external variables I'm gonna add just now. So first off, we want to define the private variables. As you can see here, we've actually defined the vactual and iactual, which is very important for implementing the system, of course. But what's also important is another important aspect is actually defining the reference variables, because it's, of course, closed loop control system. You wanna obtain a certain set point, so you have to define those as well. So I'm just gonna define them. So it's gonna be float vref equals I guess in this case it's 16.0. The vref the how do you say, the design set point, and of course you have to do the iref. I use copy and paste a lot in the code just to sort of save time, etc. And in this case I believe it's 2.133, the iref, and you want to set that up. And next, after setting up the vref and the iref, you want to set up the array for storing the variables, for the pole zero compensator, for the compensator slash controller. So first off, I'm going to define the voltage loop for the error. the voltage array for the arrow. I'll put 5 in there and initialize it to be 0. And the exact same thing is done for the and this next part is for the output, the Y part. Actually, let me show it in the Word document what was defined initially. So this is basically what we're defining, this array, this value. So first off, that was defined. So en minus 1, en. So that array is the one that was defined first. And then the m value, which is the output, is represented by the y. So that's the output array, i.e. duty cycle updates. And this value would be a maximum of 1, as is stated by the controller design. So in this case, I changed that to m. I'm not quite sure what the significance of m would be in this case, but that's what it is. It's the output. Sort of didn't want to use y. It's a bit kind of used to. Perhaps I should change it to y actually to make it align more with the Word document. Yeah. Okay, so that's e and the y. Okay, so next you do the same for the current. The first was EV. Now this is going to be EI and YI. And that's initialized to 0. And that's about it. That's basically all the initialization you need to do. First off, you initialize the Vref. Next, the current reference, the actual voltage, and the actual current. You initialize those to 0. And array for the error, for the voltage error, for the output, duty cycle change, basically the duty cycle updates. This is the array for that, 5-element array. And you do the same for the current error, and for the output duty cycle changes also for the current. And that's about it. And of course you have the array for the DMA and the ADC values. So this is basically all the initialization you need for this particular example situation. And of course I'm going to go to custom, and what you want to do is you want to add that into your custom as external variables. I've kind of gotten used to using extern because I like to access these variables from any function. Let's say I have multiple custom files. Let's say I have multiple external files. I like to access them from the main file. So extern, defining them in the main file and just including an extern in front of them in any additional C file is helps a lot for me to follow. Keep in mind that this is C code. It could be implemented in a lot of ways. I'm essentially just showing one way that has worked for me in all my implementations of closed loop control. So basically all I'm doing is I'm just adding extern to it so I can access all these variables from this particular file here. You want to do the same thing here. Extern. A lot of the code is a bit repetitive, so it's easier to just sort of copy and paste it from microcontroller to microcontroller. It's something I kind of like about it. We do the same here. Extern. Here, do the same. Extern. All right, and that's about it. And now I'm gonna get into the main part. And also, what you want to do is you want to, before you get started in anything else, you want to include certain header files because you actually implement them. You actually make use of them in this code, in the system. So first you include let's see, yeah, stdil.h. you want to just include all the necessary libraries that you might need. I sort of use the approach of just include all the standard libraries that you might need, in this case stdio. I know stdint is very crucial for typecasting, and from my experience literally nothing works without stdio.h. Yeah, stdlib. And of course you want to include the main.h and here main.h. And next math.h. Actually, in this case, math is not required. I sort of had um, there's certain scenarios where you might be implementing like an SPWM routine, perhaps. Then you would require math.h, where you would actually need to define a sign of a function, for instance. Yeah, but in this case, the math.h isn't required, from what I understand of this particular routine I'm implementing here. Yeah. So next, I'm sort of gonna go into the code itself, the routine, control routine. So, okay, the first thing that you want to do is you want to state the actual. You want to calculate it, which has actually been done in the main function. So I think I'm not gonna bother to type it again. And here by the side, you can actually see the function. So I'm just gonna go to the period elapsed callback. I'm just gonna copy the actual from there. It's very lazy, but not trying to waste time on things that have already been implemented. And next, this is sort of where you do the updates. So you want to state that yv3 3 is equals to yv2 yv2. Okay, so you sort of want to state that like that. And basically what that is, let me go back to the Word document. So basically what you're doing here is um this is the value, this is the element that you actually use to update the duty cycle, and everything else is basically history, is what was in the past. And obviously this is history 1, this is history 2, history 3, etc. So after implementing it, you need to update each one. So basically, this particular first history is going to be equated to what this is, and this is going to be equated to what this is, and this is going to be equated to that. And you have to do that constantly. You have to update the history constantly. So what we have here is actually, if you want to go deeper into digital implementations of controllers, of closed loop controllers, right? Compensators and controllers, whichever you like. It's what we have there is a what we call a velocity form system, velocity form PID controller. I really want to use the form PID controller. Think of velocity form compensator, perhaps. So there are position forms and there are velocity forms, and what the velocity form does is um, it actually implicitly keeps track of the history. So integral windup is not so much a huge problem anymore with this type of system, because it implicitly in the function itself, it just keeps track of the history. And that's sort of why I like it a lot. So that's what that is basically. I don't want to go too deep into that, anything that might sound like theory, but that's what's going on there. And essentially that's what's happening here. We're just sort of updating the output values. And of course here, so first up, the third is updated with the second updated with the first, and the first is updated with the zeroth. value of it. And of course, as you can imagine, the error is also the same for the error array. Yeah. And you might be thinking to yourself, why do I have 5 elements when I'm only accessing 3? Well, in some cases, and when you actually calculate a controller, you might require 4. You might have like a 3-pole 3-0 compensator or a 4-pole 4-0 compensator. In some applications, you go up to 10-pole 10-0 compensators. Yeah. So you probably need a bigger array, but now I just implemented that because I like flexibility to easily just add more coefficients in the future if I need to. So anyway, that's the definition. That's you're basically defining first off the output parts and then the error array. Perhaps I should separate that. And yeah. Not to worry too much about comments. I think I actually prefer that the thing is being followed because I assume you're looking at this and have something side by side there, sort of looking at it. That's how I would encourage you to use this, because that's pretty much how it would be most useful, and actually understanding implicitly, what it is that I'm saying, and the reason for each step of code is actually being implemented, and why it's being implemented the way it is being implemented. In the next stage, obviously, you wanna compute the error. And don't worry too much about the order. It doesn't matter. It's gonna happen after one another anyway, because it's essentially a loop. So what you want is v actual. Oh, my bad. It's actually vref. So it's vref minus v actual. You want to implement that, and after you implement the vref, now you want to implement the actual pi controller equation. And what I'm gonna do is I'm gonna copy this. Let's see if it works. Let's just try something interesting here. I'm gonna copy it and paste that here. Okay. So it's because I want to type it directly from what was defined in Word and the Word document. So this is YV. The first one is YV 0, and this is gonna be A3 A3V A3. I'm not sure. Maybe this wasn't such a good idea. Let me go back and just see what it is with the pawn in there. So it's 3, 2, 1, and then 1. Perhaps I should start from 1. It makes more sense that way. I'll start from the first one. So I'll just say A1 V. So A0 doesn't really exist. So you have A1, A2, A3, etc. And then B0, B1, B2, B3, B4, etc. And that's what you get. So next I'm gonna go MV, oh, not MV, Y V, and this is gonna be 1. So basically that's gonna be this element there, updating it as follows. And of course, as you can imagine, and then you have 2, gonna be A2, copy it again, A3, E, and then next thing you have E. But for the E, just keep in mind you have to change this to be 0. Of course, this coefficient should be defined up top just now. And yeah, as you can imagine, I'm just gonna copy that, paste that for 1. paste that for 2, and I define it up to 3. I mean, you know, what the hell? Why not? Just for the sake of implementing the code as stated theoretically, the Word document. So that's what you have basically. That's your duty cycle update. So that's y0 equals to the coefficient that was obtained from the octave and multiplied by the history1, a2 multiplied by history2 up the output, a3 multiplied by history3, and now to the error. So the first error multiplied by b0. So as you can see, b0, the coefficient, plays a huge role into controller performance. And of course you have b1, history1 of the error, b2, history2 of the error, b3, history3 of the error. And that's about it. And yeah, that's that. And now basically all you're doing afterwards is limiting it. So the next stage is you wanna limit the output basically. And how do you do that? So you just state if, basically an if function. So state if yv0, which is this, if that is greater than a value that will be specified. Let me say yv max. Let's say yv max. So if it's greater than yv max, you're gonna cap it off to that value. And in this case, as you can see, I use Control C a lot because it's code. It's if you want to type it out, the whole thing out, be my guest. But it saves a lot of time to just sort of copy and paste certain aspects of it. So basically what this would be, so what yv max would be most of the time is 0. You sort of want to cap it off to 0 and 1. Perhaps I should ease off of that a bit, but let me just say else if now we're looking at in the case where it's below the minimum. In this case, most likely we're literally just making sure it doesn't go negative. That's literally all the point of this is. We want it to stay between 0 and 1. That is it. And we just state, and all these things will be stated above, will be defined above. I sort of just wanted to put it into the code so you have some context before I start defining things, because I think that's very important. Context. And basically, if it's greater than the max value, make it equals to the max. If it's if it's less than the minimum value, make it equals to the minimum. And if it isn't on either extreme, just carry on as it should. And the next stage, of course, you want to update the duty cycle. CCR1 states that if we're getting CCR1, and you want to equate that to, so this is where the type casting comes in, int, and here you have to state max duty. Now this max duty varies from controller to controller, but you have to state max duty explicitly. So in this case, you want to multiply that by, because remember, we're dealing with duty cycles here, and from the controller assumes that the maximum duty cycle is 1. It doesn't assume it's like 10 or 100 or something. It assumes it's 1. And and once it gives you the coefficients, it gives you those coefficients assuming the maximum output is 1. But of course, in the microcontroller, the maximum output, duty cycle output, is not a value of 1. It's a value of 849. So you have to scale whatever you get here out of this. And to be honest, you have to scale that. Before I move on to something else, I just want to clarify. So that's the purpose of this line of code. Max duty there, it's going to be 849. You want to multiply that by 1.0. You want to scale that so you have the appropriate duty cycle. I forgot that should be TIM1. And to the next thing, this is actually why I think the STM32 microcontrollers are very high performance and really great for applications such as this, because it actually gives you a chance to write. It gives you a lot of freedom, coding freedom, to sort of write it as it is, as calculating it mathematically. Because when you're calculating it, you're getting your values in floats and in floats, and um, some microcontroller families out there do not allow you to define floats like this. Um, and the STM32 allows you to do that. Of course, you have to pay time-wise. You have to pay the price because it does take more time, but you do have that flexibility to do that. And the STM32 gives you that, as opposed to changing everything into like a 16-bit int for the purpose of time, because some microcontrollers are just not efficient in using floats. Whilst I actually calculated that this entire code on this particular microcontroller takes less than 10 microseconds, and honestly that's fantastic for executing a loop, because I've seen some pretty horrendous loop execution times on other microcontroller families that I will not mention, of course, but because they have other uses in the defense, they were designed to be used for other purposes. But anyway, my point is the STM32 is a really good microcontroller. Didn't mean to go on a tangent there, but just explaining why this is a good tool to basically use and easy to use. Um, all right, so that's basically that. It's scaled. Everything's scaled right now. It has to be defined. We have to define the coefficients and a lot of the variables that are being utilized here. So of course, the first thing to specify are the coefficients. So I'm just gonna state here define. Okay, it's wrong. Define the first variable. That's a1b. A1b, and that's gonna be 1. I'm gonna do the same because you have 3 of them: a1, a2, a3, and you can guess what the others are. It's gonna be 0. It's gonna be 0. I'm gonna copy that and paste that. Okay. I'm just gonna rename them just now. And of course, this is gonna be this is gonna be B0, B1, B2, and B3. So in this case, this is sort of where we'll go back to the Word document of the values that were calculated. So B0, let me just go back to the voltage. This is for the voltage, yeah. So this are the coefficients that was calculated. So B0 was calculated to be this. So I'm just gonna copy that, go there, paste it over there, and just go back. And then B1, I'm just gonna copy it and paste that there. That's B1. I'm just gonna save that. And other things were defined as well. Let me just state define define y0 yv max. So yv max is 1.0, and yv min, that's gonna be 0.0. And of course, max duty must be defined. Max duty is 849, and it's an integer. So it's 840, it doesn't matter. It's typecast to an integer before it's put into the duty cycle anyway. And we do not have to limit this value anymore because we've already limited yv0 to what yv max should be and yv min should be. Okay, before I carry on, I just want to state this. In terms of protecting your microcontroller, remember what was stated about um about this initially in the previous one of the previous sections. This value, this is where it sort of comes into place, into the max value that we actually implement here. This is sort of where it comes into this. This would essentially be your YV max, because this is the duty cycle into raw, in most raw form, as a ratio, as a ratio of 1. So it was said to be 0.7094. I like to go a bit higher, it's like 0.75 for instance. So essentially it will never go above 0.75, 75% duty cycle. And that's great, because if it goes to 1, if it goes past a certain point, I believe it's what, in the 90 some 90%, 95% thereabout, you're actually gonna pop your MOSFET on your microcontroller, and you do not want to do that. Okay, maybe you want to do that, but I don't want to do that. So you just sort of want to limit that value to 0.75. For me, it's evident. You should do that. So that's the purpose of that. YV max and YV min, of course, 0.0, but that's just important to take note of. From simulation, just pure simulation, you can make that 1.0, but 0.75 is a better option to use. And of course, yeah, that's defined. So essentially what you want to do next from this stage is essentially want to call this function. What did you simply want to call it? So I'm going to go back to the main. Let's go back to the main. And here, I'm just going to comment that out for a bit, because I don't need that. I think I copied that. I copied that. All right. So you simply want to do that. That's all you want to do at this point. And I'm just going to run it to see any errors, try to build it, see if we catch any errors in the system. All right, 0 errors. I just want to click on it to make sure it gets there. And I just want to add something to it. Control routine voltage. Just demarcate exactly what this is going to be for. Let me go to the custom H. Do the same thing over there. Void. All right, control routine and do that. All right, so essentially that's it. This is the moment of truth, and we'll actually see if anything was forgotten here. I'm just gonna run this very quickly because this video has sort of gone long a bit, it's gone a bit long, but longer than I hope. But let me just run this very quickly and actually see what outcome we get for VREF of 16 volts. Let me just run that. Okay. It's gonna do its thing. Okay. I'll just say cancel. Let's see. It stated that there are errors. Let me look where they are. But yeah, control routine voltage. See? Yeah. Let's run it. Okay. Okay, so it's actually successfully uploaded the code. So now I'm gonna have to pivot to the other view here. Second. Okay. All right. Flash on. and I'm gonna turn it on at this point in time. Let me just change, and there's a slight change in the main function. Yeah, so this needs to be taken out because you don't want the duty cycle being on a stuck, essentially stuck on a single line of code. All right, so let me just go back to it. Okay, flash on and turn it on. See what we get. As you can see there, it states 17.7, but there's that infamous error glitch. So I'm gonna probe it to actually just see on the multimeter, make sure it's turned on to see the actual output voltage. That's important in this case. Okay, so the actual actual output voltage is measured to be 16.36 volts. Well, I think I'll just chuck that up to resistance, the 5% resistance difference there. So as you can see, it says 17.9, but it's actually 16.35 as measured from the multimeter. So that's about it. I think in the next section, I'll deal with the system for more voltage levels, because that was what was designed for robustness. But I think this video is extended quite long. I'm just gonna end it in this particular section right here, which is basically implementing the system using basically the digital control coefficients that were calculated actually in the firmware, looking at how they're implemented in the firmware and calling that particular function and doing it. And that's essentially what this is. But in the next section, I will be changing the voltage levels to actually see if it's able to attain different voltage set points, because that is important. That was what was designed for, essentially. So yeah, and explain sort of why it's not hitting 16 volts exactly as is stated of our set points. All right, that's about it. Well, good luck in your application so far, if you're implementing this so far, and yeah, see you in the next one.